Okay, here we go.
Hi, before we get started, I wanted to show you a video made by one of our customers, Cape Horn Engineering. Cape Horn Engineering is a consultancy that is based in the UK that focuses on doing advanced CFD simulations in the sailing and leisure yacht industries. They use our software, Simcenter Aimsim Plus, almost exclusively, and I wanted to show you the types of simulations they are able to do using our product. So here what you can see is a free-running super yacht performing a circle maneuver. You can see that the rudder is executed and then they go along their trajectory. And they can calculate the advance and the transfer, as well as model both the propeller rudders and any stabilizers that they have going on. In this case, they're using virtual disks to model the self-propulsion using a constant torque, which is mimicking a constant power scenario. And they also have active rudders that give you a maximum rotation rate and maximum deflection angle to kind of understand how it's going to perform the circle maneuver. There's also dynamic stabilizers that also have a maximum rotation and rotation rate that are active during the simulation. And you can trace their rotation histories throughout the course of the simulation. So doing this, you can get a full-scale model of what is going on with this super yacht and figure out some of its free-running maneuvering characteristics, all within the computer. And with that, I want to show you how practical and simple it is to do something like we just saw. The title of this presentation is Going Beyond Calm Water Resistance Curves. My name is Miles Wheeler, and I am the Marine Application Specialist for Simcenter Aimsim. The aim of this presentation is to show you how to do advanced simulations like you just saw, and hopefully convince you that yes, you can also do these types of things. And hopefully, you'll see that it would be practical and helpful in using our tools to help you design better boats and get to better designs faster. So we at Siemens have continuously added technology to our tools over the past several years. And we think we have all of the tools necessary to help enable boat builders to simulate anything they could possibly need. First, we were able to analyze bare hull resistance calculations. Originally, we could do this with the boats fixed and do a sweep of calculations to calculate a database of resistance versus trim curves. But then we also added in dynamic fluid body interaction, or DFBI, which allows you to solve for the pitch and heave while running a resistance calculation. And then over the last few years, we've added just about every type of motion model you might need to simulate just about every type of scenario possible. We've also added several ways to model propulsor effects. We have simplified models, such as the virtual disk, that can produce the appropriate circulation and momentum distribution around the hull, so you can actually understand your hull performance quite easily with propeller effects included. Of course, we also have completely detailed models that can solve cavitation and ventilation effects while your propeller is physically rotating. So you can get as advanced or simple as you want with our propellers. And we have also added several features that would allow you to understand maneuvering characteristics. We can add in any rudders, stabilizers, control surface to help you understand how your vessel will perform in a free-running scenario. We also have dedicated modules to mimic any type of tow tank test, either at full scale or model scale. And we have also developed several ways to model waves, and we have ideas on how to handle just about any type of seakeeping scenario you may be interested in. We can model all sorts of waves, from flat water waves to simple sine waves to more realistic fifth order ocean type waves. We can model irregular sea states, and we can also superimpose just about any number of waves on top of each other. So if you want to see what a crosswell might do to affect your performance or stability, we can model that as well. But not only that, these simulations and these modules can all be combined together and done at full scale, so you can kind of see the full picture all combined together, and you can simulate just about whatever you might need to do with our product. So in this example, we can see a self-propelled boat turn under its own power in a head wave sea state. So hull accelerates from rest, encounters head waves, and then it executes its rudder, and then we can calculate the boat's trajectory. So this combines all the modules that I just mentioned, and I hope to show you how to build this exact model from a resistance calculation to this exact calculation using our product. But while we have great technology and have continuously developed techniques to allow you to simulate just about anything you might desire, the leisure craft industry has had some pushback in adopting this technology for several reasons. One, it's generally is considered to be too expensive. And calibrating the simulation is a waste of resources. Oftentimes, things are considered too complicated. How do you fully understand all the physics involved? What is the point in trying to model this when you can just go out and test it? There's always questions about the accuracy of the code. And with that, generally people think you need a simulation expert to run these types of simulations. And another kind of caveat is often people think that running a CFD takes too long. It's easier just to go out and build something and run it than to try and build a model and calibrate it and run it. And, you know, most of the boat builders have been able to build boats for decades without needing these tools, so why would you need it now? And a lot of people think, yeah, we won't use it enough, we might use it for a week and then up sit on the shelf for the rest of the year. And in general, in a small business such as boat building, there's so many things to do to build a boat, get it to market in a timely manner. Often the pushback is there's way too many other things to do, so we don't have time to do this. So the main theme is trying to integrate CFD into your design for a small leisure craft business is generally considered to be a headache that takes away from building boats. And before I took on this role at Siemens, I've worked in the boat building industry for 2 different small boat brands. I worked at a small naval architecture firm, and I completely understand the concerns here. Limited resources and budgets make the idea of taking on a brainiac exercise like a CFD simulation seem like a huge headache and oftentimes a nightmare. Let's think about this for just 1 second. Let's frame this within a context about technology that you are all likely a bit more familiar with. And that's computers. So in the early 80s, early 90s, computers were also thought of in a similar fashion. They were hard to use, they were slow, they were expensive. Who has the time to use it? And if you did want to use it, you kind of had to be a very savvy computer whiz in order to use it. But then, over the years and in the mid to late 90s, computer power and PCs became the norm in business. And it was a widely acceptable tool that you pretty much could not do business without. Email and digital communication has become the status quo, and has certainly helped us improve our productivity. I am certain that computing technology is used every day in your prospective businesses, and has made your products, and has allowed getting to your products to market even faster. And today, we have extremely fast computers that can fit in our pockets and can harness information with the push of a button. We are using apps that streamline the flow of information to make difficult and complex or tedious tasks extremely seamless. And today, we are at a similar state with our CFD technology. We can parameterize almost anything within the tool and expose just the key information via our custom trees, ensuring that you don't need to create the best practice or have a deep understanding of the numerical aspects of your simulations behind your designs. You only need to expose the key parameters, and all the sophisticated things can be hidden if desired. These apps can be created by you or by your software provider, and then you can have an app-like functionality to do your CFD simulations. This ensures all the headaches are taken out of the simulation and the same settings and best practices are applied every time you want to run a specific type of CFD simulation. So here, we can show you how easy it is to set up a standard case using our virtual tow tank template, which is available for free to customers via our support portal. So here what we can see is that we have a nice kind of guided scene that tells you what to do. So the first step is to import your hull. So here we can just open it. Since we have a scene, we don't need to create another one. And we have imported a simple prismatic planing hull. So we can now look at it, interrogate it, make sure that it is the correct hull that we are looking for. And once we're ready, we can now go to our parameters. So we have a custom scene that only exposes the parameters that you need to input. So in this case, this CAD model is built at model scale, but we want to analyze it at full scale. So we scaled it by our scale factor, which was 7. And now we have a 16-meter planing vessel, and we can now change it to run from seawater to lake water by simply updating the water type. And if we want to go to a nice warm environment, we can maybe analyze this in an 80-degree Fahrenheit temperature. So all of our fluid properties will be updated automatically, which you can see in the scene, or you can interrogate the reports. And now what we can do is we can input the draft. So in this case, the draft might be 3 feet. And you can see that it updates. And then we just need to update our speed. So in this case, we're running at 30 miles an hour. And you can type in the units in any type of unit system that you want, but it will convert it and always apply the appropriate speed. And with that, you just run the simulation. So it was pretty cool. All we had to do was input our key information, press run, and that was it. So over the next 30 minutes or so, or whatever time I have left, I plan to show you I plan to quickly highlight how planing hulls and leisure craft can be parameterized to make all of these simulations doable in a streamlined fashion, using the same base template. Here's what we will go over. The essentials behind our numerical wave tank, how to use a template to perform calm water simulations using our Design Manager tool, showcase how the template can get you to complex simulations with very few parameter changes, how to use the template to incorporate engine effects via Simcenter Aimsim coupling, also how to incorporate aerodynamic effects into your simulation, how to use our NX client to also control geometry changes within our template. And I also want to showcase how to use our Power on Cloud solutions to help you generate massive data sets very quickly to give you all the information you need in a very, very short turnaround time. So, for fast-moving hulls, such as planing hulls, the solution that we recommend is to use what we call the forced moving wave tank. This basic framework allows us to simulate just about every type of simulation one could want to do with the same CFD model. Just a few changes of parameters or some quick and easy to change models are needed to perform all types of different simulations you may be interested in. From resistance to maneuvering, seakeeping, or all of them combined, you can all do it with the same base model. Methodology uses our forced waves approach, and this allows the users to supply a wave at all boundaries in any direction by applying wave forcing around the domain. This is slightly different than your traditional setup with a fixed grid and inlet-outlet, but it proves to be more robust from a setup point of view. This is because the central part of the numerical domain solves the RANS, or the Reynolds average Navier-Stokes equations. Then the wave train is then forced through the domain on the outer perimeter. And this forced domain ensures that your wave will develop to the exact specifications, and then the RANS model will solve the actual full CFD part. Excuse me. So what this does is it allows, sorry, this needs to play. So this allows the domain to move across from any direction with the same setup. All you have to do is change one parameter, the wave propagation direction, and you can simulate any type of thing. So you can do oblique seas, you can do following seas, you can do head seas, and of course you can do beam seas, all with the same exact model. And this forcing is key because then the motion of the vessel interpolates the correct waveform regardless of its orientation. So in this video, we can see that regardless of the orientation of the moving box, which will represent where the domain of the vessel is being solved for, the wave is interpolated into the domain automatically and accurately, regardless of the orientation of the vessel. And what happens with this is now we have a completely decoupled boat motion from the wave physics, which makes it very easy to implement robust and intuitive setup of any type of wave interaction or maneuvering problems. The motions of the hull are also solved for independent of the wave setup by having two separate regions that are solved for simultaneously. So using this forced waves approach makes setup possible for doing just about anything you could want without having to rebuild your model every time you want to make a simple change. It also makes it slightly easier because for traditional CFD setups, oftentimes you have to incorporate the boat motion or some of the hull information into your wave setup. But since they're completely decoupled, everything is easy, intuitive, and very easy to implement and understand. We have also, added in a few features recently, which help improve simulations by making them faster and more robust. We have recently added in body fit overset grids that are merely offsets of your input geometry. The overset grid, in case you aren't familiar, is the grid which we will use to model the vessel motions, which is then interpolated onto the forced wave type model. So we are doing this to build grids with as few of cells as possible, and these are automatically fit to the body of interest, and then they are very free, to move easily around the domain. And the prism layers or boundary layer mesh are automatically generated, and we can solve for the pressure and shear forces accurately by quickly solving for all turbulent effects and boundary layer effects, while using the smallest domain and smallest cell size possible, which helps us significantly speed up the runs. But this body fitted mesh is then combined with our adaptive mesh approach, which we commonly call to AMR, which allows us to build the coarsest grids possible. The mesh will adapt itself to the refinement needed to capture any physical effects of the simulation, and it will adapt itself such that the interpolation between your overset grids is matched for the best accuracy and performance as possible. So what we can see here on the left is that we have our general grid. It's very coarse, and then as the free surface develops and this overset grid moves, it creates refinement around the overset grid. So we're always using as few cells as possible, but we have enough cell resolution to capture any interpolation effects or any type of physical effect that is required by the simulation. And with these tools, it is very powerful and it's making our simulations more robust and faster than they have ever been. So here's a quick video of a rendering in which we can see this AMR approach in action. So we have a prismatic pole accelerating, and we can accurately capture the bow wave and the bow splash. You can see the mesh refining wherever there's waves being developed, and you can see we get a very nice, accurate, and clean representation of the splash. This helps us use a very small number of cells. This thing runs very quickly and captures all the physics necessary. One thing I also wanted to point out is that our overset technology can be used for that is used for vessel motions can also be nested within itself. So you can have prescribed motions of rudders and or propellers that are a fixed or prescribed motion that are always working within your ship frame. So these motions will move as the ship moves. So you can have a prescribed rotation or for your rudder or for your propeller. These can be nested within the motion of your vessel. In addition to modeling propellers explicitly, we also can easily implement a virtual disk. So a virtual disk is a disk that embeds itself into your existing mesh and uses open water propeller data that your propeller supplier can give you. Or if they can't give you, you can also generate this data set easily using our CFD tools. And virtual disks are nice because they will include the swirl and momentum effects of your propeller, but it doesn't actually force you to model the propeller explicitly. So you can get all these momentum effects and swirl effects essentially for free. So it's much more computationally efficient than trying to model a propeller dynamically. And you can kind of get all your propeller effects easily using this model. We also have several motions that you can pick from using a drop-down menu. So we have free motion, which is when all the degrees of freedom are free to move in any direction, and you are dynamically solving for all the motions as a function of time. This is typically used for maneuvering or seakeeping effects when rudders and propellers are included. So you would use this type of model when trying to calculate time to plane or top-end speed predictions. We also have a forward-off maneuvering model, where we can impose speed and position trajectory in a similar way you would do in a wave basin test, and we can do that at model scale or full scale. We have an equilibrium motion model, where we can simply solve for the final steady-state position of a vessel statically, negating any transient or porpoising effects, but this calculation is much faster than trying to solve for any of the transient effects in between start and steady-state position. Excuse me. We also have several planar motion mechanisms. We can do classical rotating arm calculations, zigzag motions, and kind of just do any type of maneuver test with built-in specific modules to make your setup easy and transparent. And we also have what's called a general planar motion model as well. So here you can specify a prescribed motion in the XY plane, but then solve for the heave, pitch, and roll dynamically. So this general model could be used to run a simulation with a known fixed speed, and then calculate the relevant reactive dynamic motions of the vessel. So let's now take a deep dive on how to use this template. I showed you the video setup of a resistance run with our VTT template a few minutes ago. So while setting up a single speed was easy, it is also easy to set up a sweep of runs with our Design Manager tool. Design Manager tool is a simple right-click of an existing simulation that allows for an automated, hands-free design exploration. It can be simple sweeps, so it could be an input of desired runs, or it could be anything to a full optimization. The nice thing here is that you can set up what you want to run. Then the software will run all the jobs for you. You don't have to set up a new run by hand each and every time you want to change a boundary condition. So here's a walkthrough of how it works. So we have our existing single point simulation. We right-click. We create a Design Manager project, and then we just create a new design study. So in this case, we want to run a sweep, but of course you could choose from CAD robustness, an optimization, a design experiment, or just a manual input of runs. So here we'll do a sweep, and then what we will do is we just simply select, in this case, the vessel speed. And now we want to run a range of speeds for this vessel. And in this case, we can go from 10 to 24 knots. And if we did 0.25 knot increments, it would be 57 runs. It's a little too many. Let's just do 4 runs. And then it's doing 4.6 knots. Then we could pick any of the responses. So this is any of your data, such as resistance, pitch, trim. So of course, we'll select the pitch. Then we'll select the heave. And of course, then we can also select the resistance. And maybe we want to include the pressure and resistance forces as well. So you can break those out into their respective components. So scenes is any of the interactive visualization. So we can get 3D visualization files for any of these runs that we do. And then we have our plots, which show your transient history of any KPIs or convergence history of anything important. So it's always good measure to select all of them. And then we can simply select our run settings. So in this case, we can save all the designs, or we can just keep the KPIs. So if you want to save disk space, you don't have to save the simulations if you don't want to. And then you can figure out what computing hardware you have at your disposal. So in this case, I have 20 CPUs on my machine, and I will run one study at a time, and that's it. You just have to right click and run, and you are ready to go. So once you get your just run study, and that's it. Everything's running automatically, and you'll get your full set of resistance data. So what happens is you get the table, and in a single environment, you now have access to all single data points. So at the touch of your fingertips, you can scroll through and dynamically update your scenes, look at your plot history, look at your results. You don't have to open up a different simulation file each and every time you want to look at a different data point. So we have used the force-moving wave tank model and validated the general prismatic planing hull, or commonly known as the GPPH Hall, which was part of the 2018 MACC Simulation Grand Challenge. MACC stands for Multi-Agency Craft Conference. And the idea behind this Grand Challenge was to use numerical tools to figure out how well you could predict the resistance curve of the GPPH Hall. So using the template, in the manner in which I just described, we were allowed to run this hull and then compare it to the experimental tow tank data, which was made publicly available to the industry. And we were able to match very well, in my opinion, and we are getting within 2% difference of the experiment across a full range of speeds. So that is what I consider to be very good. Oh, shoot. Sorry. And what's even better is the average time per simulation was approximately 2 hours running on my local desktop. So my question to you then is, 2 hours may seem like a long time, but how long does it actually take to build a prototype model or even just run a model out on the lake? I bet it's quite similar. So if you could save a ton of time in prototyping costs and get accurate information, why would you not want to use this tool? It seems like it could be very helpful in changing designs very quickly. And it would allow you to explore radical ideas in a very cost-effective and timely manner to help you innovate on your products. So once you have established and validated the best practices that are giving good results in a reasonably quick turnaround time, we can then take these best practices and simply swap out the geometry within our template. So here we can take the leisure craft that I showed you earlier and analyze the resistance for this craft using the same exact settings as we did for the GPPH. That gave us a good simulation turnaround time with very good accuracy. So we can do that and just move along. And while resistance is easy, adding in waves is also easy too. So with our force-moving wave tank template, we can simply set up waves in any way we would like. So here we go, we can kind of see what's going on. So initially we ran with 0 amplitude, so we ran this in flat water to get our calm water resistance curves. But if you wanted to change to a head sea with some amplitude, maybe 1 meter amplitude, you simply update the amplitude and now you're in head seas. Pretty simple. Now if you wanted to maybe go to a wave direction change, again, you just update the one parameter for the direction change. So here we'll go to a beam sea instead of a head sea. And just like that, we're analyzing a completely different scenario. So maybe we want to go to an oblique sea. So this one would be 45 degrees relative to the bow. And maybe we also want to increase the frequency of the wave. So we can do that and initialize it. And it's just very easy to kind of set up any type of wave just by updating a few different parameters or the relevant parameters that are intuitive to a wave setup. So what you can see now is that we can easily analyze the craft in these 2 different sea states. So here we can see it in beam seas and oblique seas, and you can kind of see the corresponding difference in the vessel motions. So in the head sea, there's almost no roll motion, as would be expected. And in the oblique sea, we do get a significant amount of roll motion. You can also compare the differences in pitch and heave between these waves. So I showed you how easy it was to set up waves. But let's also see how easy it is to set up repulsor effects. So here we have our two virtual disks that are predefined in our model. These, of course, can be parameterized, so you can change the location or the diameter of these disks. And what we can do here is now we're going to enable these disks. So we go to our DFBI model, which controls our vessel motions. And now we want to include the effects or the thrust of these disks onto the vessel. So we simply just have to activate them. And before we were using general planar motion with a prescribed speed. But now since we have repulsor effects, we want to determine the speed based on the input of the propulsor. So now we just simply have to switch from general planar motion to free motion. And here you can select any motions you want to be free. So typically we may do a 3DOF calculation. So you can check any of these combinations of things you want free. But in this case, let's just do a complete 6DOF simulation. We'll leave them all checked. So what else we can do is we now look at the virtual disks. And virtual disks essentially just use your open water data. So you can import as many propeller curves as you want. And if you wanted to switch out from design A or design B or company X to company Y, you simply just have to pull the drop-down menu and select the appropriate propeller. So that way you can look at how propeller effects are affecting the performance of your vessel simply by picking the appropriate propeller from the drop-down menu. So let's kind of look at what we have now. So we just ran this head wave simulation at a fixed speed, but now we're going to run a head wave simulation under its fixed power. So if you take a look at here, before this was running a constant speed, but now you can see how the head waves affect the surge and the corresponding forward speed. You can see that's kind of oscillating about 20% as it hits the head waves. It's pretty easy to kind of compare these effects by just simply changing a few parameters and models that took just about 1 minute to do. Now, if you also wanted to add in different rudder motions, it's also pretty easy, and it's just as simple as swapping out some data. That is a simple position versus time function of your rudder angle. So here, the runs I just showed you, we have a just fixed 0-degree rudder. So it's going to go straight. The rudder is not moving throughout time. But if we want to do something like a circle maneuver, you kind of run it straight and then you press it hard over and you leave it hard over. And that's kind of the motion of a rudder that would produce a circle maneuver. Or if you want to do something dynamic or crazy, you can do, okay, let's go to starboard, let's go to port, and then we can initiate any type of motion using this rudder input that you want. So it's pretty easy. You can just swap out these CSV files or tables, and you can change your prescribed motion however you want. Now, of course, if oftentimes for maneuvering, the rudder position is a function of some other type of metric, so such as your heading, or an autopilot system, or a zigzag open ocean test. You change the rudder position whenever your heading gets to a certain point. This is also quite easy to do, simply writing a function that could be implemented into your motion based on any of the reports or KPIs that are available in the simulation. And it's just as easy to do, and it's just as robust. So here, we can put it all together, and we can see the same simulation that I showed you previously, which would run this leisure craft under its own power through head waves and executing a maneuver. So here we can see it from the side. We can see it kind of get up to speed, go through the waves. And then we can see the rudder execute. And on the right here, we can plot out its trajectory all within Star CCM+. So again, and well, I think when I showed you this, maybe at the beginning, this may have seemed like a bit daunting simulation, but I hope that you can see that just changing a few simple parameters and models, you can kind of get to a very complex simulation from a calm water resistance curve in a very straightforward and easy fashion. So a lot of people also ask how easy it is to include the aerodynamic effects. Well, our solution is always solving the air side as well as the hydrodynamic side. So for the example shown with this simple leisure craft, we can calculate the resistance based on the hydrodynamic portion or the aerodynamic portion. Or the aerodynamic portion. So in this case, the aerodynamic drag can be calculated. It was only about 1% maybe of the total drag. But this may not always be the case. And you can also include any of the effects that you want, and it's always automatically included so long as you include the appropriate geometry. So on something like a luxury yacht that has a very large superstructure, the aerodynamic loads can be critical. So again, we can include this is automatically included in our analyses, and we can plot the wake and streamlines of a parametric study. So in this case, we can analyze wind coming from any heading, and using our design manager tool, we can quickly assess all of the wake effects, flow effects, and calculate our forces on this vessel. And as you can see, using Design Manager, you can just quickly scroll through your wind direction and quickly see how that's changing the flow field, as well as what the corresponding forces are. So I think aerodynamic calculations are very easy to include in the simulation as well. So our template can also be coupled with Simcenter Aimsim. Simcenter Aimsim is our 1D code that can help you analyze things upstream of your propeller. So if you needed to incorporate your engine effects into a model, we can easily add this to the engine system to our simulation. So in this way, you could simulate a true hammer down throttle position scenario, or any model where the engine is dynamically changing. So if the engine is not under constant power and it's going through various rev cycles, various throttle positions, we can model that aspect by coupling this 1D model to a star CCM+. So this would then allow you to have a true understanding of your motor, plus your propeller, plus your hull effects as a true full system. And Aimsim has seemingly endless ways to model gas, diesel, hybrid, or electric motors. So the possibilities in swapping out engines is pretty simple. And it goes well beyond just motor modeling. Automated control systems, such as autopilots, PID controllers, or stabilizing systems, can all be modeled with Simcenter Aimsim as well, and incorporated into the 3D Star CCM+ CFD model as well. In addition, Simcenter Aimsim can also be used to kind of figure out your true gas mileage or range of your vessel by incorporating the data with different sea states or variable sea states into kind of a master model. So you can figure out the range and the efficiency for all sorts of scenarios. So if you're operating in a calm sea and then you get into a storm sea and calm sea again, you can use Aimsim to figure out how that would affect the range and maybe the efficiency of the boat over that mission cycle. That's an example. So similarly, swapping out an engine model is also pretty easy. So again, we have just our library file. So here we have an electric file incorporated to an FMU file. And FMU stands for Functional Mockup Interface, which is an industry-wide accepted platform for storing the 1D data from Aimsim. So if everything in Aimsim is labeled the same throughout the models, then we can simply swap out these FMU files. So here we swap from an electric motor to an outboard, to a two-stroke motor, to a diesel motor, all by just simply changing your FMU library file. So in this case, what we can see is we have a small power plant. It's an electric power plant. And it's going to hammer down to the 3/4 throttle position. And then we can figure out how fast the boat will go and how fast it gets to its top speed at this throttle position. So here we go, we hammer it down. We can see that the throttle is going. We get to about 3/4. Then we get up to its full speed for this small motor. And then we can plot how the propeller RPM is changing based on the input from the motor, as well as we can plot the speed versus time, so we can figure out the time it takes to get to its top end speed, which in this case is just about 6 seconds. Now, I also want to show you another thing that I also think is very cool, and that is how seamless we can integrate NX parametric CAD into Star CCM+. So here what we have is a simple planing hull. and it's been parameterized. So we have things such as lifting strike geometry, concavity, beam length, height, depth. And we can transfer all of our parameters, all any responses, so any type of mass information or CG information into Star CCM Plus through the use of our NXCAD client. So you can see that we transferred it, it created our geometry scene. It looks a bit strange, but if we turn on the mesh, we can see that it looks perfectly appropriate. It was just a weird lighting issue. And here, you can see that all of the parameters that you had in NX are now exposed at your fingertips within your Star CCM Plus environment. So now we can go through, we can change things such as our freeboard height, we can change our strike geometry, we can change the beam in this case a little bit if we wanted to. And then we will change the width of the lifting strike, make them a bit skinnier. And these are all updating CAD geometries from Star CCM Plus. Now you just simply update the model, and you get your model is changed automatically and on the fly. So this now allows you to use these imported parameters using the design with Design Manager. So now if you wanted to quickly explore how geometry changes are also affecting your design, you can quickly explore these geometry changes with our Design Manager in a seamless and completely automated way as well. And now I want to walk you through a design exploration case that we recently did, in which we went from something that would normally take several weeks, something that just took 1 hour to run in order to generate the required data needed. So here what we have is a vessel that needs a full understanding of the power or resistance requirements over a range of displacements and speeds. So what we needed to do is we needed to analyze this hull with drafts between 5.5 and 7.5 meters, as well as a understanding of speed ranges between 10 and 30 knots at all these different displacements. So if we used increments of 0.5 meter for draft and 2 knots for speed, this would equate to having to solve 55 different CFD simulations. And traditionally, that would be a bit problematic. So I think people who are used to CFD, would think that a single data point should take hours to do, and then doing a full data set for a specific weight would generally take days. And then if you need to do this over a range of displacements, you're looking at weeks to do all these CFD simulations and generate this data set. However, using Amazon Web Services cloud computing and our Design Manager tool, as well as utilizing our Power on Demand licensing scheme, and the use of this parameterized templates, which we have kind of been showcasing, we can run all of these cases. And we can do this all within an hour. So let me show you kind of how it works. So AWS allows you to set up for on-demand compute nodes, so you can build a cluster and only pay for the compute nodes as you use them. So once you build a cluster, you can easily copy files and submit the Design Manager job. It is as easy as simply typing in a simple command, and then in about 5 to 10 minutes, your cluster is built using the amount of nodes that you've requested, and all of your jobs will start running. And you can see here that we ran it, and it stopped, and it took just under 35 minutes to do. So combine that with the 10 minutes it takes to build a cluster, all of these runs were done in under 45 minutes, and certainly done with under an hour. So the results are then stored in an easily to manage file, your Design Manager project file. And you can simply just download this file back to your workstation. It's quite light and easy. You don't have to copy back gigabytes and gigabytes of data. And then you can interrogate the model using our Design Manager. So you can quickly scroll through each and every design. You can open up plots and extract any type of engineering insight within one file with all the information right at your fingertips. So this little animation kind of shows us scrolling through the designs. We have all the designs. It's quickly highlighting which resistance is, looking at the different flow field plots, looking at how the bulbous bow is affecting the bow wave generated. And again, just want to reiterate, all this was done automatically, very quickly, in under an hour. And then you have all of the key engineering data right at your fingertips in a very lightweight, easy to use file. This is my presentation. I want to thank everybody who has watched this. I think I've showed you how to use some of our advanced capabilities that are also easy to use, and you can add in a ton of fidelity into your simulations. I think I've also demonstrated how to run hundreds of jobs instead of just a few in just a matter of hours. And I hope you will agree that we are entering the next stage of the simulation world, where anybody can have access to high fidelity simulations in a very easy to use, seamless, and automated fashion. I think we have the technology to evaluate complex engineering simulations with very simple and easy to use models, and I hope that you will agree.